Hello everyone, welcome to Practical Mechanics. I'm Mohsen. Today's video is about circularity tolerance. Consider this solid shaft, size 9.8 to 10.2, and we wanted to apply circularity tolerance. The story is this. Any individual cross sections of this solid shaft must be perfect circle. But we know that producing perfect circle is not possible. Then designer consider amount of error allowance for manufacturer because he knows that manufacturer has human error, environmental error, machine error, and all these errors combine together and cause a perfect circle changes to a form like these red cross sections that you see here. Designer asks manufacturer to limit these imperfections, actually, to limit these errors. How much you deviate from a perfect circle? This is decided by the designer. Don't go more than, for example, 0.2 error. Otherwise, the part will be rejected. This is called circularity error, that a circular cross sections must lie inside a zone, which is, we call it zone shape, zone space, and the size of that is determined, for example, 0.2 by geometric tolerance. What's the effect of rule number 1 here? If rule number 1 applies to this drawing, then let's construct a table to explain it. Actual mating envelope from MMC size of this cylinder, which is 10.2, 10, 10.1, 10, 9.9, 9.8 LMC size. Geometric tolerance, circularity error. Rule number 1 says, if you produce at MMC size, it must be perfect form. All cross sections must be perfect circle. The whole object must be perfect cylinder, that we talk about it in cylindricity error. And everything must be perfect. A straightness, any surface elements or the axis of the shaft must be perfect straight, actually. Here's rule number 1 says if you produce at MMC, it must be perfect. Means no error is accepted. Zero tolerance, geometric tolerance. But if you depart from MMC, how much is the departure? 0.1 mm. You have a space for your errors. If you produce at 10, actual size of the shaft after production, you measure it and it is 10, then you deviated point, you departed 0.2 from MMC size, you have a space for your errors. And if it is 9.9, then it's 0.3, and 9.8 is 0.4 space for error. Then rule number 1 indirectly controls circularity, geometric tolerance of circularity, and geometric tolerance of circularity is within the size limit of the part when rule number 1 applied to that. Assume that besides rule number 1, in addition to rule number 1, we apply circularity tolerance, that's the symbol, and pointed to here, apply to the feature. Circularity only apply to feature, not feature of size. And we specify here geometric tolerance 0.2. Let's construct a table for different actual mating envelope size of this part, that from MMC 10.2, 10.1, 10, 9.9, 9.8 LMC size, and geometric tolerance circularity here. Rule number 1 says, if you produce at MMC, no geometric tolerance, 0 error. If you produce 10.1, okay, you have 0.1 deviated from 10.2 or departure from 10.2. Here is 0.2 departure, here is 0.3 departure. But if it was only rule number 1, you have 0.3 space for your error. But here it says that don't go more than 0.2. Here is also 0.2. And for this one, rule number 1 says you can have 0.4 error. But this geometric tolerance here, limit geometric tolerance to 0.2. Then here you will see that feature control, frame control, the sizes, and rule number 1 controls till 2. It depends on how many size we have between these two steps. Rule number 1, we can say control till here, 10.2. Circularity tolerance don't need datum. We don't use datum for circularity tolerance. Feature control frame has only 2 compartments. It can apply to both views. It can apply to the extension line between 2 views. Then it's only applied to a feature, not feature of size. And no modifier is used with circularity error. No M, no L, no phi, no P, no T, no U modifier is used with circularity error. And any individual cross sections, assume that we have this case. Any individual cross section that we cut at the object at any individual cross section, or we measure all individual cross sections, for example, this one, by CMM machine. CMM machine can give a counter of any cross sections, and we put the counter between one largest inscribed circle inside and the smallest circumscribed circle outside. This space between these 2 perfect circles is called the zone space, and the radial distance between these 2 circles is called the zone size. Then zone size here is 0.2, for example, for these cases, and zone space is the area between these 2 circles. Then, if only rule number 1 applies and no geometric tolerance is specified, we have this information for the part. If besides rule number 1 also geometric tolerance by feature control frame apply, then we have these tables. Some of the parts, some of the sizes is controlled by rule number 1, and some of them controlled by feature control frame. Thank you for watching. See you in the next video.